Welcome to The Explainer. Today we're talking about the secret ingredient that makes all of machine learning, well, work. It's this hidden assumption that lets a machine actually learn, and honestly, without it, the whole field just wouldn't exist. So let's just jump right in with a question that really gets to the heart of it all. How in the world can a computer look at just a tiny handful of examples and then turn around and make crazy accurate predictions about stuff it's never ever seen before? I mean, it feels a little bit like magic, doesn't it? But it's not.
Okay, let's make this real with a classic example. Imagine we're trying to teach a computer to guess when our friend Aldo is going to enjoy his favorite water sport. We've got this little table here with some data from the past. What the weather was like and whether he actually went out or just stayed home.
All right, now it's your turn. Just looking at the days where he said yes, can you spot the one single perfect rule that predicts what he'll do? Go ahead, take a look at those positive examples. See if you can find a pattern.
And here's where we hit a snag. The problem is, there's more than one rule that seems to fit the data perfectly. Is the rule that Aldo only goes out when it's sunny and warm? Or maybe it's just when there's a strong wind. Both of those hypotheses work for the examples we have. The data itself doesn't give us the answer. And that right there is the core issue. To make that jump from a few examples to, all possible situations, an algorithm needs something extra. It can't just rely on the data. It needs some kind of assumption, some kind of prior knowledge. So in the world of machine learning, this secret ingredient has a name: inductive bias. You can think of it as the set of assumptions that an algorithm uses to take a leap of faith. It's how it generalizes from the data it's seen to all the data it hasn't. It's basically the algorithm's built-in hunch about what the answer probably looks like.
Now, this idea is all wrapped up in what's called the inductive learning hypothesis. All this fancy quote is really saying is that we're betting that a rule that works for our training data will also work for new data out in the real world. It's a huge assumption. So with that in mind, let's go back to Aldo and see how different biases would handle this problem. All right, so for this part, the investigation, let's imagine our learning algorithms are two different detectives. They've got the exact same evidence, our training data, but their styles, their methods for cracking the case are completely different because they have two different biases.
So, meet detective number 1, the stickler. You know the type. This detective has a very, very rigid theory about how the world works. It will only even look at clues, or in our case, hypotheses, that fit its super narrow format. Anything that doesn't fit, it's immediately tossed in the trash.
And here's that bias in action. An algorithm like candidate elimination works with one simple belief. The real answer has to be a simple combination of and, like sunny and warm. It literally restricts its search to this one tiny little corner of all the possible rules out there. It's like it's wearing blinders.
So, you can probably guess what happens when the real world is a little more complicated, right? What if the actual rule is that Aldo goes out when the sky is sunny or the sky is cloudy? That's a concept with an or in it. Our stickler detective won't even consider it. It's outside its rulebook. And the result? Boom. Learning failed. The algorithm looks at the data, it looks at its strict rules, and finds absolutely zero hypotheses that fit both. The whole investigation just grinds to a halt. The stickler's rigid bias, its complete refusal to think outside its tiny box, made it fail, miserably.
Okay, so the stickler crashed and burned. Let's bring in our second detective, the minimalist. Now this one is way more open-minded. It is willing to consider literally any possible theory, no matter how wild or complex. But it does have one really strong preference that guides it. And that preference is based on a famous principle, Occam's razor. I'm sure you've heard of it. The core idea is that the simplest explanation is probably the right one. So if our detective has two theories that both explain the evidence, it's always going to lean towards the simpler one. This detective's whole style is captured in an algorithm called ID3, which works by building decision trees. Now, technically, it can create a tree for any rule you can imagine, but its bias, its preference, is for shorter, simpler trees. It builds the tree from the top, always looking for the most direct path to the right answer.
So how does it find that simplest path? Well, it starts by asking the most powerful question it can. It actually measures something called information gain to see which question does the best job of clearing things up. In this case, asking about the outlook gives it the most bang for its buck, so that becomes the very first split in its tree.
And just by following that simple rule, always prefer the simplest, most informative questions first, the minimalist detective cracks the case. It builds a neat, tidy decision tree that gets the job done without getting tangled up in rigid, preconceived notions. Its preference for simplicity led it straight to a great solution.
So, after seeing our two detectives at work, what's the verdict? What have we really learned here? Well, the single most important point is this. There's just no such thing as an unbiased learner. Every single algorithm has to have some kind of assumption to make that leap from the known to the unknown.
Let's just put them side by side. Our stickler used a restriction bias. It was handcuffed by the very language of hypotheses it was allowed to think about. It's a very hard, inflexible kind of bias. The minimalist, on the other hand, used a preference bias. It could look at everything, but it had a gentle nudge, a preference, for simpler answers. It's a much softer, more flexible approach.
And if you take away just one thing from all of this, let it be this. The goal in machine learning isn't to get rid of bias, because that's literally impossible. The real art is understanding the different biases of your algorithms, and then picking the one whose assumptions are the best fit for the real-world problem you're trying to solve.
And that, my friends, leaves us with the million-dollar question. This is the challenge that machine learning practitioners wrestle with every single day. It's so much more than just throwing data at a computer. It's about skillfully choosing a learner whose built-in prior knowledge actually matches the structure of your problem. That's how you turn this theoretical secret ingredient into real-world success.